Hi everyone. So in this unit, we are going to continue on and talk about this property of minor orthogonality, which I mentioned in the previous video. So let's say you have an m by n matrix A, and you're looking at a subset of the rows S and a subset of the column T of the same size. Then the minor of A corresponding to S and T, which we denote like that, is defined as usual, right, as the determinant of the corresponding submatrix, namely the one obtained by the rows of S and the columns of T. And if it will, if you ever ask yourself when A phi is going to be 1, right? If A of the empty set is going to be 1. Now we're going to use actually 3 theorems from linear algebra or matrix analysis that kind of maybe new, maybe not. So I'm going to just state them, but I'm not going to prove them. You can find them in any reference. So first is the Cauchy-Binet theorem, and it relates the minor for products to a product of minors. So say you have a matrix A as before, an m by n matrix, and B is an n by p matrix. So A times B is well defined. Then if you ask what's the ST minor of AB, so S is a subset of M of size K, say K, and T is a subset of P, right? That's because B is an N by P matrix. So AB is a M by P matrix, a subset of size K of P. Then the ST minor of AB is this thing. Okay, it's like the sum over all sets of size K of N. And then you take the corresponding minors, ASU, BUT. Now, if it looks like to you like with someone is doing a length 1 or 2 random walk, then that's actually true, because the way to prove this, or one way to prove this, is to look at the matrix of all minors, and then it seems like you're multiplying 2 matrices or taking a random walk, a short random walk, and that's actually exactly what you do here. But whatever, that's the theorem. Okay. So with that, we are ready to talk about what's this property of minor orthogonality. That's a property of distributions of matrices. Okay, so say you have an m by n random matrix R, namely a distribution over m by n matrices, and R is sampled according to that distribution. Then that distribution, or R, is called minor orthogonal, MO. I would use minor orthonormal, by the way, but I don't know. Minor orthogonal. If for every k and L of the right size, so k is k and L of size at most m and n, the maximum between m and n, and for every sets S and T of size k and U and V of size L, you'll see in a second where they play a role. If you look at this thing, so you sample a random matrix according to your distribution, and then you look at the ST minor of R and the UV minor of R conjugate. Okay, or transpose if everything is real in your setting. Right, so it's like okay, so that's what it is. Then minor orthogonality means, or for R to be a minor orthogonal, what you want is that this will usually be 0. It's only going to survive when S equals V and T equals U. Right, so when S equals V and T equals U, it's like orthogonality, right? Or when the matrix orthonormal, but there you're looking at entries, not subsets, and not minors, just the entries themselves. And when it's non-zero, namely when S equals V and T equals U, then it should be this normalized number, right? So that's why I like to call it orthonormal, really. But so it's whatever. It's this number that was chosen carefully. Okay. So that's minor orthogonality. That's a property of distributions. We are going to see that how random has this property, and we are going to show that some other like sign permutations have this property. Permutations don't have this property. Like random permutation doesn't have this property. But what we call a sign permutation have this property, and that property is what's kind of enough in order to kind of prove the theorem that we're trying to prove. But let's start slowly. So first of all, here's a little lemma that will be useful once or twice. So if R is a minor orthogonal, let's call it MO from now, and you take a unitary or orthogonal in the real world matrix, then also QR is minor orthogonal. Okay, so it's this property is invariant under kind of shifts. And let's prove that because it's because I want to see the proof, but also it's a good way of seeing it's a kind of a typical proof. So let's so we want to prove this thing, right? So let's fix S and T of size K, U and V of size L, and let's show that let's look at this expression when we plug QR instead of R and see that this remains true, this equality. Right, so that's the expression that we had before, but with QR instead of R. And now we are going to use Cauchy-Binet twice, once to open up this QR and once to open up this QR conjugate. So when you open this QR, right, so this is what appears here. So you add another variable W, you go over all sets of size K, let's call them W, and then you do QSW, RWT, right? This is, you put the W in the middle. And same here, you take, of course, another set Z, or it's also different size a priori. At the end, it's going to be the same size. But initially, we don't know that. So you go over all sets of size L, and you do R conjugates. I use the fact that this is R conjugate, Q conjugate, okay? So you do R conjugate UZ, Q conjugate ZV. And now, let's kind of push the expectation over R all the way and take whatever we can outside. Namely, let's exchange the order of summations, and we're first going to sum over W and Z. And okay, so the Q's will depend on those, of course, but the Q's don't depend on R. So then we are going to take the expectation over R, and we have RWT, R conjugate UZ, right? Now the point is that R is MO, so this thing is usually 0, and it's not 0 only when W equals Z and T equals U. So that's these two things. And when it's not 0, it's the number that you should kind of ignore, but know that it's there. Okay, so with that we can actually also, we know that W equals to Z, so this, because of that. So this sum actually simplifies, also K equals L, but now it's a sum only on W of size K. And what do we have left? So the fact that W equals Z was actually used in order to collapse the sum. And the fact that T equals U, let's keep it here. Let's put this delta function and also this constant. And then we are going to sum over all W's of size K over this thing, right? QSW, Q conjugate WV. And now if you look at this, but kind of in the reverse engineering, that's also by the Cauchy-Binet, it's the QQ conjugate SV minor. Right? Because when you open this up, you kind of add W of size K, QSW, Q conjugate WV. But QQ star is identity, of course, because it's from a unitary matrix. And the minor of the identity matrix is very simple, right? The minors are usually 0 unless S equals V, in which case it's 1. Right? If you don't choose exactly the same rows and columns, you'll have a 0 row, 0 column. So, so that's delta SV. And that's it, right? We have this delta TU, delta SV, this number that we carried, and this is the equality that we wanted to prove. Okay, now the second part, there is a second part. I forgot to write the second part. The second part says that also if you assume Q conjugate U equals I, then RQ is minor orthogonal, but it's all the same. Oh, so I actually didn't have to assume unitary. I only assumed that to get that. But if it's unitary, you have both of them for free, of course, and so forth. But the message is that if R is MO and you get a unitary matrix, then Q, then QR and RQ are also MO. Okay. And to get the second statement, you can either reprove it or just use the fact that if R is MO, then kind of clearly R conjugate is also MO, and then it kind of saves you the redoing things, and you can just use it as a black box what you did in the first step. Okay, so that's minor orthogonality, and I want to show really that R is minor orthogonal, but before that, and towards that, let's consider another family of distributions over matrices, which are essentially permutation, but not quite. So it's much less randomness than R, but it's more random than permutation. That's the definition of a sign permutation matrix, okay, or distribution, the distribution of sign permutation matrices. So a sign permutation matrix before the distribution is really any matrix that can be written as a permutation matrix, okay, P, but times from the left in this case, but it doesn't really matter, a diagonal with plus minus 1 entries. Okay. So if I remove this E, then I get a permutation matrix, but this E adds some more randomness, it adds the signs, hence the name sign permutation matrix. And the theorem is that a uniformly random n by n sign permutation matrix is minor orthogonal. Right? So it has this property of minors being orthogonal to each other unless they are kind of equal. Okay, so let's prove the theorem. So, all right, so what's a sign permutation matrix? So, I mean, in order to kind of work with it, in order to sample such a matrix, you have this sign vector. So it's let's call it chi, it's a plus minus 1 length n vector, and you need to also specify or sample a permutation pi in Sn. So Sn is the set of permutations on 1 to n, uniformly, of course, and independently of the signs. And then after you sample these two, then your random matrix can be obtained as by taking E high times P of pi. Okay, so now let's go by definition. So we fix S and T of size K, U and V of size L, and let's consider this expectation of minor product and see that it has the right property. So that's what we want to prove equals 0 unless S equals V, T equals U, in which case it's some number, some specific number. So let's look at this thing. So what is Q? Let's start with let's kind of open this up. So what is Q? So for Q, right, you need to sample chi and pi, and Q is then this thing. And then therefore Q conjugate is this thing, right? E high is conjugation doesn't change it. It's a diagonal real matrix, so nothing changes there. So I don't have to have a star here. Now let's do Cauchy Binet on this thing. Right, so we introduced another W. So we go over all sets W of size K, and then we take the SW minor of E chi and WT minor of P pi. And now the point is that if you look at it for a second, if S is not equal to W, then this vanishes because it's a diagonal matrix. It's like identity, but with minuses or pluses on the diagonal. It has the same feature that if you don't take a diagonal kind of set, S equals W, you will have a row of zeros or a column of zeros, which will make the determinant being 0. So really, maybe you sum over all W, but really W has to be equal to S. So what you're left with is, so this thing is going to be just the product of high I over S, right? Because you just take the product of the diagonal, and the diagonal is encoded as the high. Chi, why is it high? Chi. And P pi of WT, well, it's just, it's what it is, but now W is only S, so it's the ST minor of P pi. And the same here, right? In this thing, the only thing that's left is P pi conjugate UV times this product of the corresponding chi. Okay, but now it's with respect to this other set V, of course, not with respect to S. So taking the product of these and kind of separating because they are independent, the expectation according to chi and the expectation according to pi. I think I said chi because it's like pi and chi, and I got confused. Well, the expectation according to chi is it's this product, right? The one coming from here and the one coming from here. And the expectation over pi takes what's left, so this thing and that thing. So let's look at each individually. So this thing, it really just, you take a product of plus minuses, and unless s equals to v, things are going to vanish, right? Because if s is not equal to v, then there's going to be some I, either in s or v, that doesn't appear in the other. And it's independent, right? The signs are independent among another. So because of that, the expectation is going to be zero, right? Because you're going to take it out in the expectation, its expectation is zero, so it's going to zero out everything. But if s equals to v, then all these chi I cancel each other, and then you get zero. So anyhow, this whole thing is just delta SV. So that's what's appear here. And here, so let's look at this expression here. So we know, so I just kind of copied it and removed the conjugate and switched v and u. So this is the same as here. Here there should be a v, but let me explain why there is an s. And there should be a v and there is an s because delta SV is in front of the whole thing from before. And now note that like in the case of a diagonal matrix, now it's permutation, but it's the same thing. This diagonal, this minor p pi of st is going to be zero unless, like, all the stars are aligning, unless t equals exactly pi of s. Because otherwise, again, you're going to have a row column of zeros. Right? It's like a diagonal matrix, but just permuted. So you just need to take the minors permuted accordingly. So t has to equal pi of s, and also u has to be equal pi of s because this appears here and that appears here. So in particular, t has to be u. So what you get is delta SV from before, delta TU because of what I just said, and then these two are the same. So you get the ST minor squared. Right, and because of what I said, this ST minor is really just also a delta function comparing t and pi of s. And then you don't have to have the square, of course, because it's either 0 or 1. So now, just to recap, the expression that we are looking at now is really this thing. So it's the delta SV, delta TU, and then you have, as before here, the expectation over pi. Expectation over pi of delta t pi s. But what is this? This is precisely, so this expectation. It's precisely the probability of when you sample a pi from Sn uniformly at random, that pi of s equals to t, right? And the probability for that is 1 over n choose k, right? Because S is a set, T is a set, but pi is a permutation. So the probability, these are size k subsets of 1 to n. So the probability that will match precisely this, so at some set will be sent exactly to this other set T is just uniform over all sets of size k of 1 to the n, which is 1 over n choose k. Okay, so to summarize, we got the property that we need for minor orthogonality. And so indeed, signed permutations, not permutations, but signed permutations are sufficiently random to have this property of minor orthogonality. So with that, we're actually ready to show that Har is also a minor orthogonal, which will be key for the main theorem. So the corollary is that Har random matrix is minor orthogonal. So let's see why. So let's say that R is Har random. Then, for any fixed sign permutation matrix Q, we know that RQ is Har, right? Because sign permutations are in particular unitary. And when you take R times a unitary, you're left with the same distribution. That's the characterizing way of defining the Har measure. So for any fixed Q, which is sign permutation, RQ is Har. And so you have this equality, right? Because R and RQ have the same distribution. So whatever expectation I write for Q, I write for RQ, it's the same thing. Now, okay. Now, if Q is not just a fixed sign permutation, but if it's a uniform sign permutation, then by the theorem that we just proved, we know that Q is minor orthogonal, right? That's what we just proved. And so by the previous lemma, RQ is minor orthogonal, right? Because by the previous lemma, so let's recap it. By the previous lemma, we had that if you have a minor orthogonal and you multiply it by unitary, you get minor orthogonal. Here, I think the R and Q got switched in the use rather than in the statement of the theorem, but it doesn't really matter. Right? Q is minor orthogonal, and RQ for any R, and for any R in the R is R random, but if for any fixing of R even, R is unitary, so RQ is minor orthogonal. So anyhow, this means that this is minor orthogonal. So RQ is minor orthogonal. So this means that this thing and therefore that thing equals to the thing that we want. Delta SV, delta TU times the number, which I never remember.